Somewhere in the long story of humanity, a strange change began to happen. It did not happen in a single year. It did not happen in a single generation. No one noticed it while it was happening. Thousands of years passed. Entire civilizations rose and disappeared. Languages were born, changed, and faded away. Empires expanded across continents and then became dust. And through all of this, something inside the human head was quietly changing. The human brain was becoming smaller. Not by a tiny amount that could be ignored. Not by a change so small that scientists could dismiss it as a measurement error. Over thousands of years, the average human brain appears to have lost a surprising amount of volume. And perhaps the strangest part of all is this: nobody knows exactly why. Today, we live in a world of computers, satellites, artificial intelligence, and instant communication. We can speak to people on the other side of the planet. We can study distant galaxies. We can look deep into the structure of our own DNA. Yet when it comes to understanding why our brains became smaller after the end of the Ice Age, the answer remains uncertain. Some scientists have theories. Some think the explanation may be hidden in agriculture. Others believe it may be connected to social life. A few wonder whether the answer lies in something even deeper. But after decades of research, no single explanation has solved the mystery. And so tonight we will slowly explore this forgotten puzzle. A puzzle hidden not in a distant temple, not beneath an ancient pyramid, not inside a lost city buried beneath the sand, but inside us. Inside the story of the human brain itself. So settle in comfortably, take a slow breath, and let us travel back through thousands of years of human history, back to a time before cities, before writing, before kingdoms, before almost everything we think of as civilization. Because that is where this mystery begins. Long before anyone could record history, long before anyone could imagine the modern world, long before anyone could ask the question, why did the human brain become smaller? To understand the mystery, we first need to meet our ancestors. Not the kings and queens found in history books, not the famous names remembered by civilization, but ordinary humans, the people who lived at the end of the last ice age. Imagine a world very different from our own. Huge glaciers still covered large parts of the northern hemisphere. The climate was colder. The landscapes were wilder. Many animals that no longer exist still walked across the earth. Massive woolly mammoths wandered across frozen plains. Giant deer carried antlers wider than a person was tall. Predators moved through forests and grasslands that stretched for enormous distances. Human beings lived among them. These people were hunters, gatherers, travelers, and survivors. Every day demanded attention. Every season brought new challenges. Food could not be ordered. Water could not be turned on with a tap. Safety could not be assumed. Life required constant awareness. A hunter tracking animals across a snowy landscape needed extraordinary observation skills. A gatherer searching for edible plants needed detailed knowledge of the environment. Families had to remember migration routes, seasonal changes, dangerous locations, and valuable resources. Their world was a giant puzzle that had to be solved again and again, and their brains helped them do it. When scientists examine fossil skulls from many ancient humans, they often discover something surprising. Many of these people had brains that were, on average, somewhat larger than ours. This does not mean they were smarter. That is important to understand. Brain size and intelligence are not exactly the same thing. A larger brain does not automatically create a more intelligent person, but the observation remains interesting. If modern humans have achieved incredible technological progress, why would our brains become smaller rather than larger? At first glance, it seems backward. We often imagine evolution as a straight path: bigger, better, more advanced, more complex. But nature rarely follows straight lines. Evolution is not trying to create perfection. Evolution is not working toward a final goal. Instead, evolution responds to circumstances. If a feature helps survival and reproduction, it may continue. If maintaining that feature becomes costly, change may occur. And this brings us closer to the mystery, because brains are expensive, very expensive. The human brain weighs only a small percentage of the body's total weight, yet it consumes a remarkable amount of energy. Even while resting quietly, your brain is constantly active. Millions of processes continue every second. Memories are maintained. Signals are transmitted. Information is organized. Predictions are generated. The brain is never truly silent, and all of this requires fuel. Imagine carrying around an incredibly powerful computer every moment of your life. Now imagine that computer constantly demanding energy. That is essentially what a brain does. For our ancestors, energy was precious. Food was not guaranteed. Calories mattered. Every biological investment carried a cost. A larger brain might provide advantages, but it also requires greater maintenance. This simple fact has led some researchers to ask an intriguing question. What if smaller brains became more efficient? What if evolution found ways to reduce size without reducing effectiveness? It is an interesting possibility. But before we explore that idea further, we need to understand when this change happened. Because timing often provides clues. Scientists studying ancient skulls have gathered measurements from many different periods of history. The details can vary depending on the population being studied. Human groups around the world have experienced different histories, yet a general pattern appears again and again. After the end of the Ice Age, average brain size seems to decrease. Not overnight, not dramatically within a few generations, but gradually, slowly, across thousands of years. The timing is important because something else was happening during this period, something that would transform humanity forever. Agriculture. Today farming seems ordinary: fields of wheat, rice paddies, corn farms, fruit orchards. They are familiar parts of the modern landscape. But for most of human history, agriculture did not exist. People survived by hunting, fishing, gathering, and moving through the environment. Then, in different parts of the world, something changed. Humans began cultivating plants. They started managing animals. Gradually, communities became more settled. Villages appeared. Population increased. New social structures emerged. This transformation was one of the most important events in human history. Some historians call it the agricultural revolution, and some scientists wonder whether it might be connected to our shrinking brains. At first, the idea sounds strange. How could farming affect brain size? The answer may lie in how lifestyles changed. Imagine two different worlds. In the first world, a hunter-gatherer wakes before sunrise. The day requires constant adaptation. Weather changes, animal movements shift, food sources vary, every decision matters. Knowledge of the landscape is essential. Memory, navigation, observation, and flexibility are used continuously. Now imagine a farming village. Life is still difficult, very difficult, but many activities become more predictable. Fields remain in familiar locations. Resources are concentrated. Tasks become specialized. Instead of everyone mastering every survival skill, communities begin sharing responsibilities. Knowledge becomes distributed across groups. One person knows crops, another knows tools, another knows storage methods, another understands trade. The community itself becomes a kind of collective intelligence. This idea fascinates many researchers. Perhaps individuals no longer needed to carry as much information alone. Perhaps social systems reduced certain cognitive demands. Perhaps brains adapted to a new environment. But this theory faces challenges, because farming also introduced new complexities. Managing crops requires planning. Organizing communities requires cooperation. Trade networks require communication. Larger populations create social challenges. In many ways, civilization made life more complicated, not less, and so the mystery remained. As time passed, scientists proposed additional explanations. One of the most interesting comes from an unexpected source: ants. At first glance, ants seem very far removed from human history. Tiny insects crawling across the ground. What could they possibly teach us about human brains? Quite a lot, it turns out. Some researchers noticed something curious about social insects. In highly organized colonies, individual members often possess smaller brains than their less social relatives. Why? Because the colony functions as a collective system. No single ant needs to solve every problem. Tasks are distributed. Information is shared through group behavior. The colony itself becomes intelligent in a way that exceeds the abilities of any one individual. This observation inspired an intriguing question. Could something similar have happened among humans? Not exactly the same, of course. Humans are not ants. Human societies operate in vastly different ways. Yet as communities grew larger and more interconnected, people increasingly relied on one another. Knowledge became shared. Skills became specialized. Information could exist outside any single mind. Perhaps social complexity allowed brains to become slightly smaller while remaining effective. It is a fascinating idea, but again, the evidence remains incomplete. And every answer seems to generate new questions. Because when researchers look closely at the human story, they discover something even stranger. Despite smaller average brain size, human achievements exploded. Writing appeared, mathematics developed, architecture expanded, philosophy emerged. Science eventually transformed civilization. If brains were shrinking, why were human accomplishments growing? The contradiction sits quietly at the center of the mystery. And perhaps that contradiction contains the key. Maybe we have been asking the wrong question. Maybe the real question is not why brains became smaller. Maybe the real question is whether size was ever the most important factor at all. As time passes slowly, we begin to move deeper into the puzzle, because the next part of the story will take us inside the structure of the brain itself. And there, scientists have discovered clues that make this mystery even more surprising. The mystery becomes deeper when scientists stop looking only at skull size and begin looking at the brain itself. Because a brain is not simply a larger or smaller object. It is a network, a living landscape of connections, billions of neurons communicating through trillions of signals. Two brains can be different in size, yet similar in ability, and two brains of the same size can work in very different ways. This changes the question entirely. Instead of asking, why did human brains get smaller? Researchers began asking, what changed inside the brain during the last 10,000 years? And that is where the story becomes even more fascinating. Imagine holding two ancient skulls, one from a hunter-gatherer who lived 15,000 years ago, another from a person living in an early farming village 5,000 years ago. At first glance, the older skull may seem slightly larger, but skulls only tell us about external volume. They do not preserve thoughts, they do not preserve memories, they do not preserve intelligence. The brain itself is gone, so scientists must reconstruct the story indirectly. They compare skull measurements, they study genetics, they examine archaeological evidence. They look at diet, disease, climate, and social organization. And slowly, piece by piece, a picture begins to emerge. One important clue comes from energy. Earlier we mentioned that brains are expensive organs. But just how expensive are they? In modern humans, the brain uses roughly 20% of the body's resting energy, even though it makes up only about 2% of body weight. That is extraordinary. For ancient humans living with limited food supplies, this mattered enormously. Now consider what happened after agriculture began. At first, farming did not immediately create healthier people. In many regions, early farmers were actually shorter and less healthy than some hunter-gatherers. Their diets became less varied. They relied heavily on a few crops. Living close together also increased the spread of disease. So why would agriculture spread if it had drawbacks? Because it could support larger populations. Farming produced more food per unit of land. Villages grew, communities expanded, and over time, civilization became possible. But larger populations also changed human life in another important way. Cooperation intensified. A hunter-gatherer band might include a few dozen people. An early farming settlement could include hundreds. Later cities would include thousands, then millions. Humans became increasingly social in ways that had never existed before. And social life places unique demands on the brain. You must remember relationships, understand emotions, predict behavior, follow social rules, communicate clearly, build trust, avoid conflict. Some scientists call this the social brain idea, the proposal that human intelligence evolved largely to manage complex social groups. But here is the twist. Once societies became large and structured, individuals could rely more on shared systems. Writing stored information outside the brain. Traditions preserved knowledge across generations. Specialists handled different tasks. A blacksmith did not need to know farming in detail. A farmer did not need to understand astronomy deeply. A priest, trader, healer, or builder could focus on one domain while relying on others for the rest. Human knowledge moved outward into society itself. This is one of the most beautiful ideas in the story of civilization. The human mind did not only grow inside the skull, it expanded into culture, into language, into tools, into books, into communities, into what philosophers sometimes call the extended mind. Think about your own life. You do not memorize every phone number anymore. You do not calculate everything by hand. You rely on writing, devices, maps, and shared knowledge. In a sense, modern humans think together, and perhaps that process began long ago. But this still does not fully explain shrinking brains, because natural selection would only favor smaller brains if there were some advantage, or at least if the costs of large brains outweighed the benefits. So researchers searched for other clues. One clue came from domestication, not of humans but of animals. When wolves became dogs, they changed physically and behaviorally. Domesticated animals often become less aggressive, more social, and in some cases develop smaller brains relative to body size. This led to a provocative idea. Could humans have undergone a kind of self-domestication? The theory sounds unusual, but it has serious scientific discussion behind it. The idea is not that humans were domesticated by another species. Instead, human societies may have gradually favored individuals who were more cooperative, less violently aggressive, and better able to live in groups. Over many generations, these social pressures could have influenced both behavior and biology. Some researchers note that modern humans, compared with some ancient human relatives, have flatter faces, reduced brow ridges, and other traits that resemble domesticated animals. Could smaller brains be part of this broader pattern? It is possible, but again, the evidence is debated. And this is what makes the mystery so compelling. No single theory explains everything. Each idea captures part of the picture. Agriculture explains timing. Social complexity explains cooperation. Energy costs explain biological pressure. Self-domestication explains behavioral change. But none of them alone closes the case. Meanwhile, genetics has added another layer to the story. As scientists began studying ancient DNA, they discovered that human evolution did not stop in the distant past. It is still happening. Genes related to diet, disease resistance, skin color, and other traits have changed significantly in recent thousands of years. Human beings today are not biologically identical to humans 10,000 years ago. We are part of an ongoing evolutionary story. This realization changed how scientists think about recent history. For a long time, people imagined that evolution mostly happened in the remote prehistoric past. Then civilization arrived, and evolution supposedly slowed down. But the evidence suggests otherwise. The rise of agriculture, cities, trade, and dense populations created powerful new evolutionary pressures. Diseases spread differently. Diets changed dramatically. Social structures transformed daily life. In other words, civilization itself became an evolutionary force. And if civilization changed our genes, it could also have influenced our brains. Yet there is another subtle point that is often missed in popular discussions. A smaller brain is not necessarily a worse brain. Consider modern computers. A room-sized computer from the 1960s could perform far fewer operations than a smartphone today. Technology became smaller and more efficient. Biology is not engineering, of course, but the analogy helps illustrate an important idea. Efficiency matters. Some neuroscientists suggest that human brains may have become more specialized or more efficiently organized over time. Perhaps certain neural networks became denser. Perhaps communication between regions improved. Perhaps unnecessary volume decreased while function remained strong. The problem is that ancient brains do not fossilize. We cannot directly compare neural wiring across millennia, so the mystery remains partly hidden. And maybe that hidden quality is why the question continues to fascinate people. It touches something personal. We like to imagine ourselves as the peak of human development. We build cities, write books, and explore space. So the idea that our ancestors may have had larger brains feels unsettling. It seems to challenge the story of constant progress. But history rarely moves in a straight line. Humanity has always changed in complicated ways. We gained some things, we lost others. We became less dependent on raw survival skills, but we gained language, art, law, science, and shared knowledge systems. A hunter-gatherer from 15,000 years ago might outperform many modern people in tracking animals, navigating wild landscapes, or surviving without tools. A modern engineer might design a bridge or a spacecraft. Different worlds shape different minds. And this raises a quiet philosophical question. What does intelligence actually mean? Is it memory, creativity, problem-solving, social understanding, adaptability, wisdom? There is no single answer. The human brain evolved for life in changing environments. It evolved for survival, cooperation, and learning. And perhaps the changes of the last 10,000 years reflect not a decline, but a transformation. Still, one fact continues to linger in the background like a shadow. The average human brain did become smaller. That part is real. The debate is about why. As we move deeper into the story, we must now leave biology for a moment and enter the world of archaeology. Because buried beneath ancient settlements are clues about how human life changed after the Ice Age. And those clues may help us understand what happened inside the human mind. Long before great pyramids rose from desert sands, long before kings carved their names into stone, long before written history began, humanity experienced one of the most important transformations it would ever know. And strangely enough, the clues to our shrinking brains may be hidden there. Not in a laboratory, not in a genetic sequence, but in the remains of ancient villages. Let us travel back once again. The Ice Age is ending. The world is warming. Glaciers are retreating. Forests are spreading into regions that were once frozen. Rivers are changing their paths. Animals are adapting. And humans are adapting too. For countless generations, people had lived as mobile hunter-gatherers. They followed seasons. They followed herds. They followed opportunities. Movement was a normal part of life. A family might spend years traveling through familiar territories. The landscape itself was their home. Then, slowly, something began to change. In several parts of the world, people started staying in one place longer than before. At first, the change was subtle. A seasonal camp became a semi-permanent settlement. A temporary shelter became a sturdier structure. People returned to the same locations again and again. And eventually, some communities stopped moving altogether. The first villages appeared. To us, villages seem ordinary, but at the time they represented a revolutionary idea. For perhaps hundreds of thousands of years, humans had been travelers. Now they were becoming settlers, and settling changes everything. When people remain in one location, they begin accumulating possessions. Storage becomes important. Buildings become more permanent. Relationships become more complex. Property begins to matter. Population increases. New social rules emerge. The world starts becoming more organized, but also more complicated. Archaeologists studying some of the earliest settlements often describe them as experiments. Humanity was trying a new way of life. No one knew exactly where it would lead. No one could see cities in the future. No one could imagine global civilizations. They were simply adapting to local conditions. Yet those small decisions would eventually reshape the planet. One famous example comes from the ancient settlement of Saddle-Huruk. Located in what is now Turkey, this remarkable community existed thousands of years ago. When archaeologists first studied the site, they discovered something unusual. The houses were packed tightly together. There were almost no streets. People often entered homes through openings in the roof. Imagine standing above such a settlement. Hundreds of homes clustered together, smoke rising slowly into the sky, families living side by side, children growing up surrounded by neighbors, knowledge flowing constantly between people. This was a very different social environment from the small mobile bands of earlier times. And environments shape behavior. Behavior shapes culture. And over long periods, culture can even influence biology. The more scientists learn about early villages, the more they realize that agriculture was only part of the story. The real transformation was social. Human beings were becoming connected in new ways. Imagine a hunter living 15,000 years ago. Most people he knows belong to a small group, perhaps a few dozen individuals. He understands every relationship personally. Everyone is familiar. Everyone has a role. Now imagine a resident of a growing village. The number of people around him is much larger. Strangers become common. New social rules become necessary. Trust becomes more complicated. Cooperation expands beyond close relatives. Human society begins scaling upward. This shift may have changed the demands placed upon the brain, but not necessarily in the way we might expect. When we think of intelligence, we often imagine individual ability. One person solving problems alone. One genius making discoveries. One inventor creating something remarkable. Yet much of human success comes from collective intelligence. Groups often know more than individuals. A society can store information far beyond what any single person can remember. This idea becomes increasingly important as civilization develops. Knowledge starts spreading through communities. A potter learns techniques from older potters. Farmers share agricultural experience. Builders pass down construction methods. Stories preserve lessons. Traditions preserve skills. The community itself becomes a memory system. And once information exists outside individual minds, something interesting happens. People no longer need to remember everything personally. Think about writing. Today, writing seems normal. But imagine the first time information could be stored outside the human brain. A story written on clay. A record carved into stone. Knowledge preserved beyond memory. This was one of the greatest inventions in human history. Writing allowed information to survive generations. Before writing, every important piece of knowledge had to live inside living minds. After writing, knowledge gained a new home. Some scientists wonder whether this process gradually reduced certain cognitive pressures. Perhaps societies themselves became information storage systems. Perhaps culture absorbed tasks once handled by individuals. Perhaps the human brain adapted accordingly. The evidence remains uncertain. But the possibility is fascinating because it suggests that intelligence did not disappear. It moved. It expanded beyond the skull. And civilization became part of the thinking process. As centuries passed, villages became towns. Towns became cities. Cities became civilizations. Human cooperation reached levels never before seen. And with each step, something remarkable happened. The amount of available knowledge increased dramatically. No hunter-gatherer group could preserve the information contained within an ancient library. No single person could master everything known by a large civilization. Knowledge became distributed, shared, accumulated, layer upon layer, generation after generation. This accumulation changed human history forever, yet it also raises an unexpected question. If civilization stores knowledge externally, what happens to the brain's role? Does it become more powerful, more specialized, more efficient, or all three? Scientists still debate the answer. And while they debate, archaeologists continue uncovering clues from ancient settlements around the world. Some discoveries reveal another important piece of the puzzle: diet. Because the story of shrinking brains may not only involve society, it may involve food. At first, this sounds surprising, but remember that brains require enormous amounts of energy. Everything depends on fuel. Without energy, even the most sophisticated brain cannot function. For hunter-gatherers, diets were often extremely diverse. Different plants, different animals, fish, nuts, fruits, roots, seasonal foods, regional foods. The exact menu varied across environments, but diversity was common. Agriculture changed this. Many farming communities became heavily dependent on a small number of crops: wheat, rice, corn, barley, millet. These foods supported large populations, but they sometimes reduced dietary variety. In some regions, early farmers experienced nutritional challenges. Archaeological evidence occasionally reveals shorter average height, increased disease, or signs of nutritional stress. This observation led some researchers to wonder whether dietary changes influenced brain development over many generations. Perhaps energy allocation shifted. Perhaps biological trade-offs occurred. Again, no one knows for certain. But the possibility remains part of the larger mystery. And as often happens in science, each answer creates more questions because another puzzle soon appeared. When researchers examined human history carefully, they noticed something that seemed almost contradictory. Many ancient hunter-gatherers displayed extraordinary practical intelligence. They understood weather patterns, animal behavior, plant identification, navigation, tool making, survival strategies. Yet they left behind relatively little technology compared with later civilizations. Meanwhile, people living in agricultural societies eventually created mathematics, engineering, astronomy, and writing. So which lifestyle required greater intelligence? The question itself may be flawed. Perhaps intelligence simply adapted to different challenges. A hunter's mind, a farmer's mind, a merchant's mind, a scholar's mind, each developed within a unique environment. And environments shape abilities. Even today, human skills vary dramatically depending on experience. A sailor sees patterns in the ocean that others miss. A musician hears details hidden within sound. A carpenter notices structures invisible to untrained eyes. The brain changes according to what it repeatedly does. This flexibility is one of humanity's greatest strengths. It allows us to adapt, and adaptation may be the central theme of this entire story. Perhaps shrinking brains were not a sign of decline. Perhaps they reflected changing demands, changing environments, changing societies, changing ways of living. But before we accept that possibility, we must examine another surprising clue. A clue hidden not in villages, not in agriculture, not even in civilization, but in the skulls of our ancient relatives. Because when scientists compared modern humans with earlier human species, they discovered patterns that make this mystery even more difficult to explain. And those patterns may force us to rethink what brain size really means. As time passes slowly, our journey continues deeper into the past, far beyond farming, far beyond the first villages, toward ancient humans whose lives were very different from our own. And there, waiting quietly among the fossils, another piece of the puzzle begins to emerge. The deeper we travel into human history, the stranger the mystery becomes. At first, the puzzle seemed simple. Modern humans have slightly smaller brains than many humans who lived thousands of years ago. Interesting, certainly, but perhaps not shocking. Yet when scientists pushed further back into the past, they found something even more surprising. Some ancient human relatives possessed brains that were as large as ours, and in some cases, even larger. This discovery forced researchers to ask an uncomfortable question. If bigger brains automatically create greater intelligence, then why are those ancient humans no longer here? Why did their species disappear while ours survived? The answer suggests that brain size alone cannot explain human success, and that realization may be one of the most important clues in the entire mystery. Let us step back hundreds of thousands of years. The world looks very different. Modern cities do not exist. Agriculture has not yet appeared. No books have been written. No monuments stand on the horizon. Yet humans are not alone. Different human species share the planet. For most of our history, Homo sapiens was only one branch of a much larger family tree. Today, we are the sole surviving human species. But in the distant past, there were others. One of the most famous was Neanderthals. For generations, Neanderthals were misunderstood. Popular culture often portrayed them as crude, slow, or unintelligent. A kind of primitive human unable to compete with modern people. But scientific discoveries have painted a very different picture. Neanderthals survived in harsh environments for hundreds of thousands of years. They created tools. They hunted large animals. They cared for injured group members. They controlled fire. And evidence suggests they may even have practiced symbolic behavior. In many ways, they were remarkably capable. But one fact continues to surprise many people. The average Neanderthal brain was often slightly larger than the average modern human brain. At first glance, this seems confusing. If larger brains mean greater intelligence, shouldn't Neanderthals have dominated? Yet history unfolded differently. Modern humans spread across the globe. Neanderthals disappeared. Clearly, something more complicated was happening. Scientists began examining not only size but organization, because brains are not empty containers. Different regions perform different functions. The arrangement matters. The connections matter. The efficiency matters. Imagine two cities. One city covers a larger area. The other is smaller but more efficiently designed. Which functions better? The answer depends on organization. The same principle may apply to brains. Researchers studying fossil skulls have suggested that some differences between modern humans and Neanderthals may involve how brain tissue was allocated. Certain regions may have emphasized different tasks: vision, motor control, social processing, planning, communication. The exact details remain debated, but the broader lesson is clear. Size alone does not tell the whole story. And once that lesson is understood, the mystery of shrinking brains begins to look different. Perhaps we have been focusing on the wrong measurement. Perhaps what matters most is not how much brain exists, but how it is used. This idea becomes even more interesting when we look at another pattern found throughout nature. Across many species, evolution often favors efficiency, not maximum size, not maximum complexity, efficiency. Nature rarely rewards waste. If an organism can achieve the same result using fewer resources, that can be advantageous. Birds provide a useful example. Flight demands extraordinary energy efficiency. Every unnecessary gram matters. As a result, birds evolved lightweight skeletons and highly specialized anatomy. The goal is not maximum size. The goal is effective performance. Similarly, brains are costly organs. If evolution can maintain or improve function while reducing energy requirements, that may provide advantages. This possibility has led some scientists to imagine human evolution as a process of optimization, not simply growth, not simply expansion, but refinement. A gradual reshaping of biological systems to meet changing conditions. Yet the evidence remains incomplete, and another mystery soon enters the story. A mystery involving children. Because when scientists study human development, they discover something extraordinary about our species. Human childhood is unusually long. Compared with many animals, humans spend a remarkable amount of time learning. Years, even decades. We are not born with all the knowledge we need. Instead, we absorb information from our environment. Language, customs, skills, technology, culture. This learning process is one of humanity's greatest strengths, and it may help explain why culture became so important. Imagine a child born into a hunter-gatherer group. That child gradually learns tracking, navigation, tool use, local ecology, social rules, and survival skills. Now imagine a child born into a farming village. The knowledge differs: agriculture, storage, trade, community responsibilities. And later, in more advanced societies, children learn writing, mathematics, history, and countless specialized skills. The brain evolved not only to think, it evolved to learn. And as human societies became increasingly complex, learning itself may have become more important than raw brain volume. A slightly smaller brain connected to a rich cultural system might outperform a larger brain operating alone. This possibility fascinates many anthropologists because it suggests that intelligence may be distributed across generations. Every child inherits not only genes but accumulated knowledge. Each generation begins where previous generations ended. Culture becomes a second inheritance system, one biological, one cultural. Together, they shape humanity, and perhaps civilization changed the balance between them. As knowledge accumulated externally, brains may have adapted to different roles, not necessarily less intelligent, simply different. Yet there remains a stubborn fact that scientists cannot fully explain. The decrease in average brain size appears relatively recent. Most of the reduction occurred within the last several thousand years. This timing continues to attract attention because it overlaps with major changes in human society: agriculture, urbanization, writing, governments, trade networks, population growth, the rise of civilization itself. It seems unlikely to be a coincidence. But proving exactly how these changes influence biology is difficult. Human history is complicated. Many forces operate simultaneously: Climate changes, diseases spread, diet shifts, migration occurs, social systems evolve. Separating one cause from another is extraordinarily challenging, and so researchers continue searching for clues. Some look at genetics, others examine archaeology, others study comparative biology. Each discipline contributes pieces of the puzzle, but no one yet possesses the entire picture. Perhaps that is what makes this mystery so enduring. Unlike many historical questions, it does not have a clear ending. There is no lost artifact waiting to be discovered, no hidden inscription that reveals the answer. The evidence must be assembled slowly from fragments scattered across thousands of years, and each fragment reveals only part of the story. As time passes, another fascinating possibility begins to emerge. What if the shrinking brain is not the most important change that occurred? What if another transformation happened at the same time, one so profound that it reshaped the human experience itself? A transformation involving language, because language may be the closest thing humanity possesses to a superpower. It allows one mind to share ideas with another. It allows knowledge to survive death. It allows civilizations to build upon the discoveries of previous generations. And some researchers believe language may hold crucial clues to understanding how smaller brains could coexist with greater cultural achievements. So now, let us move a little deeper into the story, away from fossils, away from skull measurements, and into the invisible world of words. Because there, hidden within language itself, another piece of the mystery may be waiting. Imagine waking up tomorrow in a world without language, not just without books, not just without phones, without language itself. No words, no names, no stories, no explanations, no conversations. You could still see, you could still hear, you could still think, but sharing complex ideas with other people would become almost impossible. Many of the things we take for granted would disappear overnight. Science, history, laws, education, technology, civilization itself. All of these depend on one remarkable ability: the ability to transfer knowledge from one mind to another. And that ability may help explain one of the greatest mysteries in human evolution, because language changed everything. Long before cities existed, humans were already speaking. Exactly when language first appeared remains uncertain. It does not fossilize. Archaeologists cannot dig up ancient conversations. No stone tool preserves a sentence. No skeleton records a spoken story. Language leaves very few traces behind, yet its effects are visible everywhere. At some point in the distant past, humans developed an extraordinary capacity to communicate complex ideas. Not merely warnings, not simple signals, but detailed information, experiences, plans, memories, dreams, knowledge. Once this ability emerged, something profound happened. Information could travel between individuals with incredible efficiency. A person no longer needed to learn everything through direct experience. They could learn from others. Imagine two ancient hunters. One discovers a dangerous cliff hidden beyond a valley. Without language, every person might need to encounter that danger personally. With language, a single discovery can protect an entire community. Knowledge becomes transferable. Mistakes become lessons. Experience becomes collective. And collective knowledge changes the rules of survival. Some scientists argue that this was one of the most important turning points in human history. Because once information could move efficiently between people, intelligence became partly social. The smartest group was not necessarily the one with the largest brains. It was the one that shared knowledge most effectively. This idea is worth considering carefully. When we think about intelligence, we often imagine individuals, a brilliant inventor, a great philosopher, a gifted scientist, but many human achievements are collective. No single person invented civilization. No single person created modern science. No single person built all human knowledge. Instead, knowledge accumulated slowly, generation after generation, person after person. Language made this possible. A child could learn from parents. Students could learn from teachers. Communities could preserve discoveries. Ideas could survive beyond the lifespan of their creators. In a sense, language allowed humanity to create a shared memory, and shared memory is powerful. Imagine trying to rebuild modern civilization from scratch. One person could never do it. Even the most intelligent individual lacks enough knowledge. But millions of people working together can achieve extraordinary things. Civilization itself is a network of shared information, and language is the system that connects it. This realization has led some researchers to an intriguing possibility. Perhaps cultural evolution gradually became more important than biological evolution. For most animals, adaptation occurs mainly through genetics. Changes happen across generations, slowly, over long periods of time, but humans developed another pathway: culture, knowledge, learning, tradition, language. These systems allow adaptation to occur much faster. A new tool can spread within years. A new idea can spread within months. A useful technique can transform entire societies. No genetic change is required. The information simply moves through culture. And once culture becomes powerful enough, it begins influencing evolution itself. This relationship is complex but fascinating. Imagine a society that develops better food storage. More people survive, population grows, social structures change, new opportunities emerge, all because of an idea. The idea alters the environment in which humans live, and that altered environment creates new evolutionary pressures. Culture changes biology. Biology supports culture. The two systems influence each other continuously. This feedback loop may be one of the defining features of humanity, and it may help explain why smaller brains did not prevent enormous cultural achievements, because intelligence was no longer confined to individuals. It became distributed across communities, across generations, across civilizations. Yet language itself raises another question. If communication became increasingly important, did the brain reorganize to support it? Some scientists believe so. The human brain contains specialized regions associated with language processing. These regions allow us to understand speech, construct sentences, and communicate ideas. But language is not merely about words. It also involves abstraction, planning, symbolic thought, imagination, the ability to discuss things that are not physically present. A hunter can describe tomorrow's journey. A parent can tell a story about the past. A teacher can explain something never personally experienced by the student. Language allows minds to travel through time, and that ability is extraordinary. It means that knowledge can accumulate far beyond individual lifetimes. Every generation inherits not only genes but information. Stories become lessons. Lessons become traditions. Traditions become culture. Culture becomes civilization. And civilization becomes a giant storage system for human knowledge. The more researchers study this process, the more they realize that the human brain evolved within a cultural environment unlike anything found elsewhere in nature. Other animals learn, some even teach, but humans create vast networks of shared information. Libraries, schools, universities, books, records, maps, mathematics. These systems dramatically expand what a society can know. And once they exist, the role of individual memory changes. You do not need to remember every detail personally. You only need to know where information can be found. Think about your own life. You probably do not memorize thousands of historical dates. You do not remember every scientific formula. You do not store every fact inside your head. Instead, you rely on external systems, books, computers, databases, other people, civilization itself. This reliance on shared knowledge is incredibly efficient. But it also changes how intelligence operates. Success increasingly depends on accessing information rather than memorizing everything personally. Some researchers believe this shift may represent one of the most important developments in human history, and perhaps over thousands of years, it influenced the evolutionary pressures acting on the brain. Again, no one knows for certain, but the possibility is difficult to ignore, especially when we consider another curious observation. The period during which brain size decreased overlaps with a period during which cultural complexity increased dramatically. Agriculture expanded, cities grew, trade networks connected distant regions, writing systems appeared, mathematics advanced, religious traditions developed, governments emerged, knowledge accumulated faster than ever before. If intelligence were simply a matter of brain volume, this pattern would seem contradictory. But if intelligence depends heavily on networks of communication and shared information, the picture becomes much clearer. Humanity may have become collectively smarter even as average brain size decreased. It is a subtle distinction, but an important one, and perhaps it reveals something profound about our species. Maybe the true power of humans is not individual intelligence. Maybe it is collective intelligence, the ability to cooperate, the ability to communicate, the ability to build upon the discoveries of others. A single human can achieve remarkable things, but millions of humans sharing knowledge can transform the world. This idea changes how we think about evolution. Instead of viewing intelligence as a property contained entirely within one brain, we begin seeing it as something larger, a network, a system, a conversation stretching across generations. And that conversation has been continuing for thousands of years. Even now, it continues. Every book ever written, every lesson ever taught, every story ever told, all are part of the same process, a process that began long ago around campfires where ancient humans shared knowledge through spoken words. Yet despite all this, the mystery remains unresolved. Language explains many things, but it does not completely explain shrinking brains. The puzzle still contains missing pieces, and one of those missing pieces may be hidden within something even more fundamental, something that affects every living organism: energy. Because every biological system must obey the same basic rule. Resources are limited. Every advantage comes with a cost. Every adaptation involves trade-offs. And when scientists began examining those trade-offs, they uncovered another possible explanation for the shrinking human brain, an explanation involving survival itself. As time passes slowly, we now move deeper into the hidden economics of evolution. A world where every calorie matters, every biological investment has a price, and where the human brain, remarkable as it is, may have faced pressures few people ever consider. There is an old rule that quietly shapes all life on Earth. Nothing is free. Every feather on a bird, every antler on a deer, every muscle in a predator, every leaf on a tree, all of it requires energy. Nature is constantly making calculations, not with numbers, not consciously, but through the slow process of evolution. Every trait carries a cost. Every advantage demands resources, and few organs are more expensive than the human brain. Tonight, as we continue exploring the mystery of shrinking brains, we arrive at a surprisingly simple question. What if the brain became smaller because nature found a cheaper way to achieve the same result? At first, this idea sounds almost too simple, but sometimes the simplest questions lead to the deepest discoveries. Imagine an ancient human living 12,000 years ago. Food is uncertain, weather changes unexpectedly, predators remain a threat. Survival depends on finding enough energy every day. Calories are precious. Nothing can be wasted. Now imagine carrying an organ that constantly consumes enormous amounts of fuel, even while resting, even while sleeping, even while sitting quietly beside a fire. That organ is the brain. The human brain is one of the most energy-hungry structures ever produced by evolution. Although it represents only a small fraction of body weight, it demands a remarkable share of the body's energy supply, and it never truly turns off. Even during sleep, countless processes continue. Memories are organized. Signals travel through neural networks. Connections strengthen and weaken. Patterns are maintained. The brain is always working. This constant activity provides tremendous benefits. But it comes at a cost, and throughout evolutionary history, costs matter very much. One of the most influential ideas in biological science is the concept of trade-offs. A trade-off occurs when improving one feature requires sacrificing something else. For example, an animal might develop larger muscles. That can improve strength, but larger muscles require additional energy. The benefit comes with a price. Similarly, a larger brain may provide advantages. Yet maintaining that brain requires resources. If resources become limited, evolution may favor efficiency. Not necessarily bigger, not necessarily smaller, simply more efficient. This possibility has fascinated researchers for decades. What if shrinking brains were not a sign of reduced capability? What if they were evidence of optimization? The idea becomes especially interesting when we examine human history after the Ice Age. As agriculture spread, diets changed dramatically. In some places, food became more predictable. In others, nutritional diversity decreased, populations expanded, diseases became more common, living conditions transformed. The human body had to adapt to entirely new circumstances, and adaptation often involves compromise. Imagine a community transitioning from hunting and gathering to farming. The new lifestyle allows larger populations. More children survive. Villages grow. Civilization begins to emerge. But the environment also changes. People spend more time performing specialized tasks. Knowledge becomes distributed across communities. Social systems become increasingly important. Under these conditions, the pressures acting upon the brain may have shifted. Perhaps maintaining extremely large brains was no longer worth the energy cost. Perhaps slightly smaller brains offered advantages in terms of efficiency. No one knows for certain. But the theory remains compelling because it aligns with a broader pattern found throughout nature. Evolution often favors organisms that achieve results economically. Nature does not reward waste. If two solutions work equally well, the less costly solution frequently wins. This principle can be observed everywhere. Birds evolve lightweight skeletons for flight. Fish develop streamlined bodies for swimming. Desert plants conserve water with extraordinary efficiency. Life constantly searches for balance, and perhaps the human brain was no exception. Yet there is another layer to the story, because energy does not only affect the brain, it affects the entire body. Throughout human evolution, different organs have competed for resources. Muscles require energy. The immune system requires energy. Growth requires energy. Reproduction requires energy. Everything draws from the same limited budget. Some scientists refer to this as the body's energy economy. And like any economy, resources must be allocated carefully. This perspective leads to an intriguing possibility. What if changes elsewhere in the body influence the brain? For example, as human societies became larger and diseases spread more easily, immune systems may have faced new challenges. Agricultural communities often experienced greater exposure to infectious diseases than small hunter-gatherer groups. Living close together created opportunities for pathogens to spread. The body may have needed to invest more energy in defense. Could this have influenced evolutionary pressures on other organs? Possibly. Again, certainty remains elusive, but such questions reveal how interconnected biological systems really are. Nothing evolves in isolation. Everything influences everything else. The brain is part of a larger organism, and the organism exists within a larger environment. Changes in one area ripple outward. A shift in diet affects health. Health affects survival. Survival influences reproduction. Reproduction influences evolution. The chain continues endlessly. As researchers explored these ideas, some began comparing human evolution with developments in technology. The comparison is not perfect, but it offers a useful analogy. Imagine an early computer from the mid-20th century. It occupies an entire room. Massive machinery fills the space. Enormous amounts of electricity are consumed. Yet its capabilities are limited compared with modern devices. Now consider a smartphone, much smaller, much more efficient, far more powerful in many respects. Technology did not simply become larger, it became better organized, more efficient, more refined. Some scientists wonder whether biological systems occasionally follow similar principles, not through engineering, not through design, but through evolution. Perhaps the human brain became more efficient over time. Perhaps certain neural networks improved. Perhaps communication between regions became optimized. Perhaps the same tasks required less volume. The challenge, of course, is proving such ideas. Ancient brains do not survive. Researchers must infer patterns indirectly. Skulls provide clues, genes provide clues, archaeology provides clues, but many details remain hidden. and hidden details leave room for mystery. That mystery becomes even more intriguing when we consider another fact. Human intelligence appears remarkably flexible. A person can learn mathematics, or music, or navigation, or language, or engineering. The same basic organ performs an astonishing range of functions. This flexibility suggests that organization may matter more than sheer size. A well-organized network can achieve extraordinary results, and perhaps that network continued evolving even as overall volume decreased. Yet if efficiency explains everything, why did ancient humans possess larger brains in the first place? This question brings us back to the environments in which they lived. The world of hunter-gatherers demanded constant adaptation, tracking animals, reading landscapes, remembering seasonal patterns, monitoring dangers, navigating enormous territories. These tasks may have favored different cognitive strategies than those required in agricultural societies. Perhaps larger brains offered advantages under those conditions, and perhaps those advantages became less important as civilization developed. Again, this remains speculative, but it fits a recurring theme in evolutionary history. Traits evolve in response to specific environments. When environments change, selection pressures change as well. The qualities that once provided advantages may become less critical. New demands emerge. New adaptations follow. Human history after the Ice Age was a period of enormous environmental change. Not merely climate change, social change, technological change, cultural change, economic change. Every aspect of life was transforming. And within that transformation, the human brain may have been changing too, slowly, quietly, generation by generation. Yet despite all these theories, one puzzle refuses to disappear. The reduction in brain size was real, but human achievements continued growing. Civilizations expanded, knowledge accumulated, technology advanced, art flourished. Science eventually emerged. If smaller brains represented a disadvantage, why did human success continue accelerating? The answer may lie in something we have only touched upon so far, the emergence of collective intelligence. Because perhaps the greatest invention in human history was not a tool, not agriculture, not writing, not even language. Perhaps it was cooperation itself. And if cooperation truly transformed humanity, it may explain why individual brain size became less important than ever before. As time moves gently forward, we now approach one of the most fascinating ideas in the entire mystery. An idea suggesting that human beings succeeded not because any single brain became larger, but because millions of brains learned to work together. And once that happened, the rules of evolution may have changed forever. Imagine standing on a hill overlooking a great ancient city. The sun is rising. Smoke drifts upward from hundreds of homes. Merchants prepare their goods. Farmers arrive from surrounding fields. Builders begin their work. Children run through narrow streets. Priests prepare ceremonies. Craftsmen shape wood, stone, and metal. Everywhere people are busy. At first glance, it looks like thousands of separate lives unfolding at the same time. But if we look more closely, something remarkable appears. None of these people survives alone. Each depends on countless others. The farmer grows food. The potter makes containers. The builder constructs homes. The trader moves goods. The healer treats illness. The teacher shares knowledge. Every individual performs only part of the larger task, and together they create something extraordinary, a civilization. This may seem obvious today, but in the story of human evolution, it represents one of the greatest transformations ever to occur. For most of human history, survival depended heavily on individual knowledge and the knowledge of small groups. Then societies grew, communities expanded, and humanity began operating as a network, a giant system of shared intelligence. Some scientists believe this change may be one of the most important clues in the mystery of shrinking brains. Because once knowledge becomes distributed across society, individual minds no longer carry the entire burden alone. Think about something simple. Imagine you suddenly needed to build a modern airplane. Could you do it? Almost certainly not. Even highly educated people could not because they lack intelligence, but because no single person possesses all the necessary knowledge. Modern achievements depend upon cooperation. Engineers understand one part, physicists understand another, manufacturers contribute different expertise, pilots provide practical experience. Thousands of people participate. The airplane exists because knowledge is distributed across a network. Human civilization functions in much the same way, and that network has been growing for thousands of years. The result is something astonishing. Human societies know vastly more than any individual human ever could. A single person may understand only a tiny fraction of modern science. Yet society as a whole possesses an immense reservoir of information. In a sense, civilization has become a kind of collective brain. Not literally, but functionally. Information is stored, shared, updated, preserved, passed forward, and this collective intelligence may have altered the evolutionary landscape in profound ways. To understand why, let us imagine two different worlds. In the first world, knowledge exists only inside individual minds. If a skilled hunter dies, much of his knowledge disappears. If an experienced healer dies, valuable information vanishes. Every generation must rediscover many things. Progress remains slow. Now imagine a world where knowledge can be shared efficiently. Skills are taught, lessons are recorded, mistakes become educational tools, discoveries accumulate. The next generation begins where the previous generation ended. This creates a powerful advantage. Knowledge compounds, much like interest accumulating in a bank account. Each generation adds a little more, and over centuries the results become extraordinary. This process may explain why cultural complexity expanded so rapidly despite shrinking average brain size. The power was shifting from individuals to systems, from isolated minds to connected minds, from personal knowledge to collective knowledge. And once that shift occurred, human capabilities grew dramatically. Consider writing. Earlier, we discussed how writing allowed information to exist outside the brain, but its impact may have been even greater than that. Writing allows communication across time. A person can share ideas with people who do not yet exist. Think about how remarkable that is. An author writes words, centuries pass, empires rise and fall, entire civilizations disappear, yet the information survives. A conversation continues across generations. This ability transformed humanity. Knowledge no longer depended entirely on memory. Libraries became external storage systems. Records preserved discoveries. History became cumulative, and cumulative knowledge is incredibly powerful. Some researchers describe human civilization as an information processing system. The comparison may sound technical, but the basic idea is simple. Civilizations gather information, store information, organize information, transmit information, use information to solve problems. In many ways, that resembles what brains do. And perhaps this resemblance is not accidental. Perhaps cultural systems gradually assumed some of the functions once handled primarily by individual minds. If so, the evolutionary pressures acting on brains may have changed accordingly. Again, certainty remains impossible, but the theory fits several observations, and it helps explain a paradox that has puzzled scientists for years. Why did human achievement continue increasing while brain size decreased? Because perhaps intelligence itself was changing form, not disappearing, transforming, expanding beyond biology. This possibility becomes even more fascinating when we examine how modern humans actually solve problems. Very few of us work entirely alone. Scientists collaborate, engineers collaborate, doctors collaborate, teachers collaborate, researchers build upon previous discoveries. Every major achievement rests upon layers of accumulated knowledge. Even the simplest modern object reflects countless contributions from countless people. Take a pencil. It appears ordinary, yet creating one requires wood processing, mining, transportation, manufacturing, design, and distribution. No single person performs all these tasks. The object exists because society coordinates specialized knowledge. And if a pencil requires collective intelligence, imagine the complexity involved in creating a spacecraft, or a computer, or a modern city. Humanity's greatest strength may not be individual brilliance. It may be cooperation. The ability to connect minds together, the ability to share information, the ability to build systems larger than ourselves. This idea changes how we think about evolution. Traditionally, people imagine evolution shaping individuals, and of course it does, but humans are unusual. We create environments that influence future generations. We build institutions. We preserve information. We develop technologies. Culture becomes part of the evolutionary process. Some scientists call this gene-culture coevolution, a complex interaction between biology and culture. Genes influence behavior, behavior creates culture, culture changes environments, changed environments influence evolution. The cycle continues, and over thousands of years, small effects can produce major consequences. Perhaps shrinking brains emerged from such interactions, not because intelligence became less important, but because intelligence became increasingly distributed, shared, externalized, embedded within social systems. The more we examine human history, the more plausible this possibility appears. Yet another mystery waits nearby. Because even if collective intelligence explains part of the story, it still leaves unanswered questions. For example, why did the reduction occur when it did? Why after the Ice Age? Why during the rise of agriculture and civilization? And perhaps most intriguingly, why did the trend not continue indefinitely? After all, if smaller brains were always advantageous, why didn't they continue shrinking dramatically? The answer suggests that evolution is not moving toward a single destination. Instead, it is constantly balancing competing pressures, advantages and disadvantages, costs and benefits, trade-offs and opportunities. The human brain exists within that balance, and understanding that balance may require us to look beyond history itself. because the next clues come from a surprising source. Modern neuroscience. Scientists studying living brains have uncovered discoveries that challenge many traditional assumptions about intelligence. Some findings suggest that size may matter far less than we once believed. Others hint that organization, connectivity, and efficiency could be the real keys. And if those discoveries are correct, then the mystery of shrinking brains may be leading us toward a much larger question. What exactly is intelligence? As evening settles gently over our imaginary ancient city and countless minds continue working together beneath the fading light, we move forward once more, toward the modern age, toward the laboratories of neuroscience, and toward a deeper understanding of the most complex object known to exist in the universe, the human brain itself. For a long time, people believed that understanding intelligence would be simple. Measure the brain, compare the size, find the answer. It seemed reasonable. After all, larger brains contain more tissue, more neurons, more potential processing power. Surely that must explain everything. But as neuroscience developed, researchers discovered that reality was far more complicated. The brain is not like a storage box. It is not simply a matter of volume. A brain is a living network, and networks are often defined not by size but by connections. To understand why this matters, imagine two cities. One city covers a huge area. The other occupies less space but has excellent roads, transportation systems, and communication networks. Which city functions more efficiently? The answer depends on organization. The same principle may apply to brains. A larger brain can be useful, but if communication between regions is slow or inefficient, size alone offers limited advantages. Meanwhile, a smaller but highly connected brain may perform remarkably well. This realization transformed neuroscience. Researchers began looking beyond overall volume. They studied neural pathways, information flow, connectivity, specialization, patterns of activity, and what they discovered challenged many old assumptions. Intelligence appears to emerge from the way brain regions work together, not simply from how much brain tissue exists. This may seem obvious now, but it changed the entire discussion. Because if intelligence depends heavily on organization, then shrinking brains become less mysterious. A smaller brain does not necessarily mean reduced capability. It may simply reflect different architecture, different priorities, different evolutionary pressures. Consider another example from nature. Birds often possess surprisingly impressive cognitive abilities despite having relatively small brains. Some species can solve problems, use tools, recognize individual faces, plan for future events. For years, scientists struggled to understand how such small brains could accomplish so much. The answer appears to involve neural density. Certain bird brains pack enormous numbers of neurons into compact spaces. In other words, organization matters, density matters, efficiency matters. Size alone tells only part of the story. This lesson may also apply to humans. Unfortunately, ancient brains do not survive for direct examination. Researchers cannot compare neural density between modern humans and people who lived 10,000 years ago. The evidence simply does not exist, yet the principle remains important. When discussing shrinking brains, we must be careful not to assume shrinking intelligence. The two are not necessarily the same, and this distinction leads us toward a deeper question. What exactly do we mean by intelligence? At first, the answer seems straightforward: the ability to solve problems, the ability to learn, the ability to reason. But the more scientists study intelligence, the more difficult it becomes to define. A mathematician displays one kind of intelligence. A musician displays another. A hunter tracking animals across difficult terrain demonstrates yet another. A skilled diplomat, surgeon, teacher, or engineer each relies on different combinations of abilities: memory, creativity, pattern recognition, social understanding, adaptability, planning, communication. All contribute to intelligence in different ways, and evolution does not necessarily optimize every form simultaneously. Instead, different environments reward different skills. This idea becomes especially relevant when comparing ancient and modern humans. Imagine placing a modern office worker into a wilderness environment with no technology, no maps, no GPS, no supermarkets, no modern tools. Many people would struggle. Now imagine placing an experienced Ice Age hunter into that same environment. The outcome might be very different. The hunter possesses skills perfectly adapted to that world: navigation, observation, tracking, resource management, environmental awareness, abilities refined through generations of experience. Does that mean the hunter is more intelligent? Not necessarily. It means intelligence is context dependent. Different environments reward different capacities. And as environments change, the forms of intelligence most valuable for survival may change as well. This realization may be central to understanding the shrinking brain mystery. Because the world transformed dramatically after the Ice Age, agriculture appeared, settlements expanded, social structures grew more complex, knowledge accumulated, technology advanced. The challenges facing humans changed, and changing challenges often lead to changing adaptations. Perhaps larger brains offered advantages in highly mobile hunter-gatherer societies. Perhaps different traits became more important within agricultural civilizations. Perhaps efficiency and social coordination gained greater value. The evidence remains incomplete, but the pattern is plausible, and it aligns with a broader understanding of evolution. Nature does not reward absolute superiority. Nature rewards fitness within specific environments. A trait that proves valuable in one setting may become less important in another. Evolution responds accordingly. This perspective helps explain many apparent contradictions in human history. For example, modern humans generally outperform ancient humans in tasks involving accumulated knowledge: science, engineering, medicine, technology. But those achievements depend heavily on cultural inheritance. No individual invents them alone. Meanwhile, ancient humans often possessed survival skills that many modern people lack entirely. Again, intelligence did not disappear, it adapted. And adaptation may be the key theme running through this entire story. Yet neuroscience has revealed something even more intriguing. The human brain remains astonishingly flexible. Researchers call this neuroplasticity, the ability of the brain to change itself, to reorganize, to strengthen certain connections, to weaken others, to adapt continuously throughout life. This flexibility allows humans to learn extraordinary ranges of skills: languages, music, mathematics, sports, art, technology. The same brain can support countless different forms of expertise, And perhaps this flexibility became increasingly important as societies grew more complex. Instead of evolving highly specialized instincts for every challenge, humans rely heavily on learning. We adapt culturally. We learn from one another. We absorb knowledge from our environments. This strategy is remarkably powerful, and it may help explain why culture became such a dominant force in human evolution. The brain evolved not only to know things, but to learn things, to adapt, to absorb information, to cooperate, to participate in collective intelligence. Viewed from this perspective, the shrinking brain mystery begins looking less like a story of decline and more like a story of transformation. But there is still one major piece missing, a piece that has fascinated scientists in recent years. Because while researchers were studying ancient skulls, genetics, archaeology, and neuroscience, another field began offering unexpected insights: the study of human evolution itself, specifically the realization that evolution never stopped. Many people imagine evolution as something ancient, something that happened to distant ancestors, something largely finished. But the truth is far more interesting. Human evolution continues, even today, and understanding that ongoing process may provide some of the most important clues yet about why our brains changed during the last 10,000 years. As time moves quietly forward, we leave the laboratory behind. We leave measurements and scans behind, and we enter the unfolding story of evolution itself, a story that is still being written. A story in which every human alive today remains a participant. And somewhere within that story, another piece of the mystery may finally begin to reveal itself. When most people hear the word evolution, they imagine something distant, a world of ancient fossils, strange creatures, primitive ancestors walking across forgotten landscapes. It feels like a story that belongs entirely to the past, a story that ended long ago. But evolution did not end. It never ended. In fact, one of the most surprising discoveries of modern science is that human beings are still evolving. Right now, at this very moment, the process is slow, far too slow to notice within a single lifetime. Yet across generations, changes continue accumulating. Genes spread, genes disappear, populations adapt. The story goes on. This realization changed how scientists think about the mystery of shrinking brains. Because if humans were still evolving during the rise of civilization, then brain changes could not simply be dismissed as ancient history. They might represent part of a larger evolutionary transformation, a transformation still unfolding today. To understand why this matters, imagine the life of a human living 20,000 years ago. The environment is harsh. Food sources vary. Injuries can be deadly. Predators remain dangerous. Weather shapes nearly every aspect of survival. Now compare that world with life inside an early agricultural village. The challenges are different. Food production becomes central, population density increases, diseases spread more easily, social relationships become more complex, property appears, trade develops, conflict changes, the environment has been transformed. And when environments change, evolution often follows. This principle is simple but powerful. Evolution does not respond to the past. It responds to current conditions. The traits most useful in one environment may differ from those most useful in another. As human societies changed, the pressures shaping our species changed too. Researchers studying ancient DNA have uncovered remarkable examples of this process. One famous case involves milk. For most mammals, the ability to digest milk disappears after childhood. Yet some human populations evolve the ability to digest dairy products throughout adulthood. Why? Because certain societies began raising animals and consuming milk regularly. A cultural practice created a new evolutionary opportunity. Over time, genes supporting adult milk digestion became increasingly common in some regions. Culture influenced biology. Biology responded. This is one of the clearest examples of gene-culture coevolution, and it demonstrates something important. Human evolution can be driven by changes we create ourselves. We alter our environment. Then our environment influences us. The cycle continues. The same principle may have affected the brain. Agriculture changed diets. Cities changed social structures. Writing changed information storage. Technology changed daily life. Each innovation created new conditions, and those conditions may have shaped evolutionary pressures acting upon the human mind. Yet evolution rarely produces simple answers. Traits interact, systems overlap, causes combine. The shrinking brain mystery likely involves many factors rather than one single explanation. This complexity frustrates scientists, but it also makes the story fascinating. Because reality is rarely simple. Imagine trying to explain why a city exists. You could point to geography, or economics, or history, or politics, or culture. All contribute. None alone provides the full answer. The same may be true for shrinking brains. Agriculture contributed. Energy efficiency contributed. Social complexity contributed. Culture contributed. Perhaps genetics contributed. Each factor may represent part of a much larger picture, and the picture becomes even more intriguing when we consider another possibility. What if some changes happen not because larger brains became disadvantageous, but because certain aspects of human life became safer? For much of human history, survival demanded constant vigilance. Every day involved uncertainty. Every journey carried risks. Every meal required effort. Modern societies, despite their own challenges, often provide greater stability. Food storage improves security. Medical care reduces mortality. Social institutions provide support. The environment changes. And when environments become less demanding in specific ways, evolutionary pressures may weaken. Traits once essential for survival may no longer face the same selective forces. This idea remains controversial, but it illustrates how complex evolutionary explanations can become. There is rarely one cause. Instead, multiple influences interact across long periods of time. And because these changes occur slowly, they often remain invisible to the people living through them. Imagine trying to notice a mountain eroding. Day by day, the change seems non-existent. Yet over thousands of years, entire landscapes transform. Human evolution works much the same way, generation after generation. Tiny changes accumulate. The effects become visible only when viewed across vast stretches of time. This is why the shrinking brain mystery remained hidden for so long. No one living 10,000 years ago could observe it happening. The process was far too gradual. Only modern science, comparing ancient remains with modern populations, revealed the pattern. And once the pattern appeared, the questions followed. Why did it happen? What does it mean? What does it tell us about ourselves? The answers remain incomplete. Yet perhaps that incompleteness is valuable. Not every mystery must be solved immediately. Sometimes the search itself teaches us something important. In this case, the search reveals how interconnected human history truly is. Biology influences culture. Culture influences biology. Environment influences both. Nothing exists in isolation. The story of the human brain is not merely a biological story. It is also a cultural story, an environmental story, a technological story, a social story, a historical story, all woven together. And perhaps that is why the mystery has resisted simple explanations. The brain did not evolve separately from civilization. It evolved within civilization. The two stories became intertwined. As villages became cities and cities became civilizations, humanity changed, not just externally, internally as well. The changes may have been subtle. The changes may have been gradual. But they were real, and they continue today. Even now, researchers debate how modern technologies may influence cognition, how digital tools affect memory, how information networks affect attention, how artificial intelligence may alter the way humans solve problems. These questions remind us of something profound. The relationship between humans and their environment never stops evolving. The process continues. New technologies create new pressures. New pressures create new adaptations. The story remains unfinished, and perhaps that is the most important lesson of all. We often think of ourselves as the final chapter, the completed product of evolution. But evolution has no final chapter, no ultimate destination, only change, continuous change, endless adaptation. And nowhere is that truth more visible than in the history of the human brain. Yet before we move further, another fascinating question emerges. A question that sits quietly beneath everything we have discussed so far. If brain size decreased, and civilization expanded, and intelligence transformed, then what exactly did our ancestors possess that we may have lost? Because every adaptation involves trade-offs. Every gain comes with a cost. And some researchers wonder whether the ancient human mind experienced the world in ways modern humans rarely do. Ways that may reveal another hidden dimension of this extraordinary mystery. There is a quiet assumption that often shapes the way we think about history. The assumption is that every step forward is simply progress, that modern humans are better at everything, smarter in every way, more capable in every situation, more advanced in every sense. But history rarely works like that. Every gain comes with a trade-off. Every new ability changes something else. Every transformation creates both advantages and losses. And when scientists study ancient humans carefully, they sometimes wonder whether our ancestors possessed certain strengths that modern people rarely experience. Not because they were superior, not because they were more intelligent overall, but because they lived in a different world. A world that demanded different skills. Imagine waking up before sunrise 10,000 years ago. There is no clock, no calendar hanging on a wall, no weather forecast, no smartphone, no artificial light. The landscape itself becomes your source of information. You notice the position of the stars, the direction of the wind, the movement of animals, the smell of rain before it arrives, the subtle changes in vegetation. Tiny details become important, very important, because survival depends on them. An experienced hunter-gatherer may notice patterns invisible to modern eyes, tracks in the soil, broken branches, changes in bird behavior, signs of distant water. The environment becomes a language, and reading that language requires attention, constant attention. Some anthropologists who have lived among traditional hunter-gatherer groups describe extraordinary observational abilities. People notice details that outsiders miss entirely, not because they possess magical powers, not because their brains are fundamentally different, but because years of experience have trained them to pay attention. The brain adapts to what it repeatedly does. And over generations, cultures shape what people learn to notice. This raises an interesting possibility. Perhaps some forms of practical intelligence became less important as civilization developed, not because they disappeared completely, but because technology gradually assumed many of their functions. Consider navigation. For most of human history, people navigated using memory, landmarks, stars, rivers, mountains, and environmental cues. Today, many people rely on digital maps. The destination appears on a screen. Instructions are provided automatically. The technology is incredibly useful, but it changes the cognitive demands involved. Skills that were once essential become optional. Something similar has happened with memory. Ancient societies often depended heavily on oral traditions, stories, genealogies, songs, historical accounts. Important knowledge had to be remembered. Sometimes vast amounts of information were stored entirely in human memory. Professional storytellers and oral historians could preserve astonishing quantities of detail. Today, much of that information lives outside the brain, in books, databases, servers, digital archives. Again, this is enormously useful, but it changes the role memory plays in daily life. The pattern appears again and again throughout history. Tools expand our capabilities, but they also reshape how we use our minds. Writing reduced the need to memorize certain information. Calculators reduced the need for complex mental arithmetic. Maps reduced navigational demands. Computers transformed information storage. Artificial intelligence may be creating new changes even now. Each innovation solves problems, yet each innovation also alters cognitive habits. The brain adapts accordingly. This adaptability is one of humanity's greatest strengths, but it also means that intelligence is always changing, not disappearing, changing. And perhaps something similar happened during the transition from hunter-gatherer societies to agricultural civilizations. Different environments rewarded different skills. Different skills influenced behavior. Behavior shaped culture. Culture shaped learning. Learning shaped the brain. The cycle continued. Yet there is another possibility worth considering, a possibility involving attention itself. Modern life is full of information, messages, screens, notifications, advertisements, news, entertainment. The average person encounters more information in a single day than many ancient humans may have encountered in weeks. This abundance creates opportunities, but it also creates challenges. Attention becomes fragmented. Focus becomes difficult. The brain constantly shifts between tasks. Ancient environments were demanding in different ways, but they often contained fewer competing streams of information. A hunter tracking an animal for hours must maintain sustained attention. A gatherer searching for edible plants must observe carefully. A navigator crossing unfamiliar terrain must remain aware of countless environmental cues. The cognitive demands differ from those of modern life. Neither is necessarily superior. They are simply different, and this difference reminds us of something important. The human brain evolved to adapt. It is not fixed. It responds continuously to circumstances. The abilities most emphasized in one environment may fade in another. New abilities emerge. Old abilities become less central. The process never stops. This brings us back to the mystery of shrinking brains, because perhaps the question is not what became smaller. Perhaps the deeper question is what became different. The answer may involve attention, memory, social interaction, learning, culture, cooperation, energy efficiency, language, technology. Each factor contributes part of the story, and together they reveal something fascinating. The human brain is not merely a biological organ. It is part of a system that includes culture, tools, language, and society. As those systems changed, the brain changed too, not necessarily for better, not necessarily for worse, simply differently. And that realization challenges one of the oldest assumptions in human history, the assumption that evolution always moves in a straight line. In reality, evolution behaves more like a winding river, sometimes expanding, sometimes narrowing, sometimes changing direction entirely. The path depends on circumstances, not destiny. The shrinking brain mystery may be one example of that principle, a reminder that change does not always look the way we expect. And perhaps that is why scientists continue studying it, because beneath the measurements and theories lies a larger question, a question about what it means to be human. How much of who we are comes from biology? How much comes from culture? How much comes from the environments we create? And how much remains hidden within the countless generations that came before us? As we move quietly forward, another chapter of the mystery begins to emerge, a chapter involving one of the most surprising discoveries of recent science, the possibility that the future of human intelligence may depend less on individual brains than on the networks connecting them. And if that possibility is true, then the story of shrinking brains may not simply be about the past. It may also be a clue about where humanity is heading next. And so, after traveling across thousands of years of human history, across the end of the Ice Age, the birth of agriculture, the rise of villages and cities, the growth of language, culture, and civilization, we arrive at the end of our journey, but perhaps not at the end of the mystery. Because despite decades of research, countless studies, and extraordinary advances in science, no one can yet say with complete certainty why the human brain became smaller during the last 10,000 years. The evidence is real. Ancient human skulls suggest that average brain volume gradually declined after the end of the Ice Age. That part of the story is well supported. The mystery lies in understanding exactly why it happened. Was it agriculture? Was it changing diets? Was it energy efficiency? Was it growing social complexity? Was it self-domestication? Was it the rise of culture and collective intelligence? Or was it some combination of all these forces working together over thousands of years? The truth is that we do not yet know. And perhaps that uncertainty is what makes the mystery so fascinating, because history often gives us clear endings. A city is built, an empire falls, a civilization disappears, a battle is won, a discovery is made. But some questions remain open. The shrinking human brain is one of those questions. The deeper scientists investigate, the more they discover that the answer is probably not simple. Human beings are not simple. We are the product of biology and culture, of genes and ideas, of instincts and imagination, of evolution and history, all working together. And perhaps the story of the shrinking brain reveals something important about how we think about intelligence itself. For generations, many people assume that bigger must mean better. A larger brain must mean greater intelligence. A smaller brain must mean less. Yet the evidence does not support such a simple conclusion. During the very period when brain size was gradually decreasing, human achievements were expanding. Language flourished, writing appeared, mathematics developed, art evolved, architecture transformed landscapes, science eventually emerged, civilizations connected continents, knowledge accumulated across generations. The human story became more complex than ever before. This suggests something profound. Intelligence is not merely a matter of size. It is a matter of organization, connection, adaptation, learning, cooperation, and perhaps most importantly, sharing knowledge. A single human brain is remarkable, but what truly changed the world was not one brain. It was millions of brains working together, every story told around a fire, every lesson taught from parent to child, every discovery preserved in writing, every idea passed from one generation to the next. Together, they created something larger than any individual mind, a collective intelligence stretching across centuries. And perhaps that collective intelligence became one of humanity's greatest evolutionary advantages. The story of the shrinking brain may therefore be less about loss and more about transformation. Not a decline, not a failure, but a change. A shift in how intelligence operated within our species, from isolated survival toward cooperation, from individual memory toward shared knowledge, from small groups toward civilizations, from biological adaptation alone toward culture and technology. And yet, even after everything we have explored, one quiet question remains. What would it be like to meet one of those ancient humans? A hunter from 15,000 years ago, a traveler crossing vast landscapes, a person whose brain may have been slightly larger than ours. Would they seem familiar? Would they think like us? Would they understand our world? Or would we discover that intelligence can take forms we rarely imagine? Perhaps we will never know. But the question itself reminds us of something valuable. Human history is not a story of becoming completely different from our ancestors. It is a story of continuity. They are still with us, in our genes, in our languages, in our traditions, in our curiosity, and in the remarkable brains we carry today. Brains that remain among the most complex objects known in the universe. Brains capable of asking questions about themselves, capable of studying their own history, capable of wondering why they changed, and capable of finding beauty in mysteries that remain unsolved. So as our journey comes to a gentle close tonight, we are left not with certainty, but with wonder. 10,000 years ago, something began changing inside the human head. The change was slow, almost invisible, generation after generation, century after century, millennium after millennium, until one day modern scientists noticed the pattern and began asking why. The answer remains incomplete, but perhaps that is fitting, because some of the most interesting questions are not the ones we solve immediately. They are the ones that continue inviting us to look deeper, to remain curious, to keep exploring, and to remember that even after all our discoveries, there are still mysteries hidden within the story of being human. And somewhere, Deep inside the quiet history of our species, the shrinking brain remains one of them. Good night.